Today, we are going to learn about the limit of a function. And first, I'm going to introduce the intuitive idea of limits. Then we are going to see how we can use tables and graphs to estimate limits. We are also going to learn about infinite limits and how they give rise to vertical asymptotes. And we are going to end this class talking about two examples of oscillating functions and how to evaluate limits when we have an oscillating function. Let's start with this example where we have to evaluate the limit of x squared minus x plus 2 as x goes to 2. We know that this function is a quadratic function, so we know that the graph of this function is going to be a parabola, and because the number that is multiplying x squared is 1, which is positive, the parabola is going to be concave up. So we can sketch the graph of this function, and then we are interested in knowing what happens to the function as x approaches 2. Well, notice in this sketch of this graph that as x approaches 2, f of x is approaching 4. And then this is represented in this graph by the two pink arrows. Last time, we were using also tables to estimate limits, and we're going to do the same in this example. So we can take numbers of x that get close to 2. So the numbers in the left, they are close to 2, but they are less than 2. And the numbers in the right column, they are approaching 2, but they are bigger than 2. So if we evaluate f of x for those values of x, those are the numbers that we are going to obtain. Notice in the second column that the numbers, they are approaching 4. So the biggest one is 3.99. And then in the last column, the numbers are also approaching 4, with the last entry being 4.003. So it seems reasonable to say that as x is approaching 2, based on the graph and also in this table, it is reasonable to say that the limit of this function as x goes to 2 is equal to 2. When we evaluate the limit of a function as x goes to a number a, what we are asking is, what is happening with f of x as x is going to a? So this gives rise to this intuitive definition of a limit. Let's suppose that we have a function f of x that is defined when x is near the number a. What do we mean by that? It means that we are interested in an open interval that contains a, but maybe the function is not defined at a itself. So we write this expression, limit of f of x as x goes to a equals L, and we can read it like this, or we can say the limit of f of x as x approaches a equals L. Then this is going to be true if we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a. Well, going back to our previous example where the function f of x was defined by x squared minus 2x plus 2, what does it mean to say that the limit of f of x as x goes to 2 is equal to 4? Well, based on our intuitive definition of a limit, it means that we can make the values of f of x as close to 4 as we want by replacing x values sufficiently close to 2, but not equal to 2. Once again, we have the graph of the function f of x, and I want you to notice that as x approaches 2, f of x is approaching 4, which is actually the value of the limit. So when we evaluate limits, we are interested in knowing what happens with f of x. So we are looking at the y values of the function as x approaches the given number. In this case, x is approaching 2. Now let's see how we can use tables to estimate limits. Let's consider this example where we have the function given by sine of x over x, and we want to evaluate the limit of this function as x goes to 0. So if we are going to use a table, we have to evaluate uh, the function at numbers close to 0. So we have here two tables. On the left one, we have numbers that are getting close to 0, but are bigger than 0. And on the right table, we have numbers that are approaching 0, but are less than 0. So notice, for example, that in the left table, we start with an approximation of 0.84. And as we get closer and closer to 0, so in the last line, for example, we have that the approximation is 0.99. And on the right table, similarly, we start with an approximation that is 0.84. And then as we get close to zero, um, if we consider, for example, x equals 0.001, f of x in this case is going to be 0.99. So based on the values that we got in the previous two tables, we can estimate that the limit of sine of x over x as x goes to 0 is equal to 1. And then just to make sure that our estimate is correct, we can plot the graph of this function in an app like GeoGebra. And then we are going to see that we were correct, because if x approaches 0, either from the left or from the right, we are going to see that the graph of the function is approaching 1. In general, we can find the limit of a function as x approaches a using its graph by looking at the heights of points whose x values get closer and closer to a. And it can be from either side, either from the left or from the right. If the heights of the graph, they approach a given number L, then we say that the limit of the function as x approaches a is equal to L. Otherwise, we say that the limit does not exist, and we write DNE for short. It can be the case that the function is going to approach one number from the left and a different number from the right. In this case, we say that the limit does not exist. When we evaluate the limit of a function as x approaches a given number, it means that we want to know what's happening with f of x as x is approaching that given number. In other words, we are looking for the y values of the function as x approaches the given number. And the next GIF is going to illustrate this. Like I said in the previous slide, as x goes to a number, the values of f of x, they can be different if we consider approximations that happen from the left and from the right. This motivates the definition of one-sided limits. Saying that the limit of f of x as x goes to a from the left is equal to L means that we can make the values of f of x as close to L as we want if we take values of x that are close to a but less than a. And similarly, we have a definition of right-hand limit. Now we consider that the values of x are greater than a. Let's take a look at this example where we have the graph of a function f, and we want to evaluate some limits of this function. So the first one is the limit of f of x as x goes to -2. So we consider an open interval containing -2, and we want to know what happens with f of x. So notice that either from the left or from the right, the graph of the function is approaching this point, which has height 1. So the limit of f of x as x goes to -2 is equal to 1. Next, we want to evaluate the limit of f of x as x goes to -1 from the left. So we're going to consider an open interval containing -1, but we are interested in knowing only what happens for values less than -1. So as we approach -1 from the left, the function is approaching this open ball, which has height 0. So the limit of the function as x goes to -1 from the left is going to be equal to 0. We want to evaluate next the limit of the function at the same point -1, but now we are approaching from the right. So approaching from the right means that we are getting numbers bigger than -1, and the function is approaching the same open ball, which has height 0, so the limit is going to be equal to 0. Notice that the answer to letters B and C are equal to 0, so the side limits of the function as x goes to -1, they're both equal to 0. So the conclusion is that the limit of the function as x goes to -1 is equal to 0. Now let's take a look at the limit of the function as x goes to 1, first from the left and then from the right. Well, first from the left, let's consider this open interval containing minus 1. And if we are approaching from the left, it means that we are considering values of x less than 1. So the graph of this function is approaching 0. So this limit is going to be equal to 0. Now, if we consider an open interval containing 1, but we are approaching now from the right, we observe that the graph of the function approaches this open ball here, and this open ball has height 1, so the limit of f of x as x goes to 1 from the right is going to be equal to 1. And because the one-sided limits, they are different, then the conclusion is that the limit of the function f of x as x goes to 1 does not exist. What about the limit of the function as x goes to 0? Let's consider the one-sided limits, and let's start with the left-hand limit. As x goes to 0, from the left, f is increasing, and the graph is almost becoming a vertical line. So we denote this fact by writing limit of f of x as x goes to 0 from the left is equal to infinity. And similarly, if we consider now the limit of the function as x goes to 0 from the right, we are going to observe that the function is decreasing, and also the graph of the function is almost becoming a vertical line. So we are going to denote this by writing the limit of f of x as x goes to 0 from the right is equal to minus infinity. When I gave the intuitive definition of a limit, I said that the graph of the function had to approach a specific real number L for the limit to exist, which is not the case here. So we say that neither limit exists because their heights do not approach any particular real number. So to give the complete information, we will write that limit of f of x as x goes to 0 from the left is equal to infinity, so the limit does not exist. And similarly, the limit of f of x as x goes to 0 from the right is minus infinity, so the limit does not exist. This last example motivates the intuitive definition of an infinite limit. If we have a function f that is defined near a, then saying that the limit of f of x as x goes to a is equal to infinity means that we can make the values of f of x as large as we want and positive by taking values of x that are sufficiently close to a. And then we have a similar definition for negative infinity limit. To help us understand what's going on, thinking of the following example is usually helpful. What happens when we divide 2 by ever smaller positive numbers? So we can start dividing 2 by 1, and we're going to get 2. But then if we divide by 0.01, we're going to get 200. And if we keep decreasing the number by which we are dividing 2 and making it close to 0, the result is going to be every time bigger and bigger. So it appears that the result is becoming larger without bound, and it's increasing toward infinity. Let's take a look at this example where we have to evaluate the limit of this function as x goes to 1 from the right. Well, as x goes to 1 from the right, the numerator is going to go to cosine of 2 pi times 1, which is the same thing as cosine of 2 pi, which we know from trigonometry that is equal to 1. Now let's consider what happens with the denominator. We have here the graph of the denominator, which is 1 minus x, and then we are considering that x is approaching 1 from the right. So let's consider an open interval containing 1. But now, because we are approaching from the right, it means that we are considering numbers of x that are actually bigger than 1 only. So as x goes to 1 from the right, the graph of the function is going to approach this number here, which has height 0. But because the graph of the function is below the x-axis, we say that it approaches 0, but it's negative. So this is what we have. The limit of this function is going to be minus infinity because the numerator goes to a number, a positive number, which is 1, and the denominator goes to 0, but actually it's approaching from numbers that are less than 0. So it's like we are dividing a positive fixed number by a number that is close to 0 but negative. So as we saw in the previous example, when this happens, when we are dividing a number by another number that is getting closer and closer to zero, but is less than zero, then we have minus infinity. And because it's minus infinity, we say that the limit does not exist to give the complete information. In this example, we are given the graph of f, and we want to evaluate some limits. The first one is the limit of f of x as x goes to minus 2. So we take an open interval containing minus 2, and we want to see what happens with the graph of the function. Well, we observe that both from the left and from the right, the graph of the function is approaching this point, which has height 1. So the limit of f of x as x goes to minus 2 is equal to 1. In the next two examples, we want to evaluate the limit of f of x as x goes to minus 3, but let's consider first as x approaches minus 3 from the left. So we take an open interval containing minus 3, but we are considering only numbers that are less than 3. We observe that the graph of the function is approaching this open ball, which has height 1, so the limit of the function as x goes to minus 3 from the left is equal to 1. And now we take numbers bigger than minus 3, and we observe that it's actually approaching this closed ball, which has height 0. So the limit of the function as x goes to minus 3 from the right is equal to 0. And we observe that the side limits, even though they exist, they disagree. They are different. So the conclusion is that the limit of f of x as x goes to minus 3 does not exist. And the reason is, like I said, because the side limits, they are different. In the last three items, we want to evaluate the limit of the function as x goes to 1. Let's start by taking a look at the limit of this function as x goes to 1 from the left. So let's take an open interval containing 1, but we are going to restrict our attention to values that are less than 1. So as x approaches 1 from the left, the graph of the function is decreasing, and the graph of the function is almost becoming this red dashed line. So we say that the limit of the function as x goes to 1 from the left is equal to minus infinity. And because minus infinity is not a number, to give the complete information and the complete answer, we have to state that it's equal to minus infinity, so it does not exist. Now the limit of the function as x goes to 1 from the right. We consider an open interval containing 1, but now we are taking a look at numbers that are only bigger than 1. It looks like the function is oscillating a little bit, but we can see that it's actually approaching this, this closed ball here, which has height 0. So the limit of the function as x goes to 1 from the right is going to be 0. Now, because the one-sided limits of the function as x goes to 1 are different, the conclusion is that the limit of the function as x goes to 1 does not exist. We saw some examples of functions where the graph of the function was very, very close to vertical lines. Those lines, they are called vertical asymptotes. And here is the formal definition of vertical asymptotes. The vertical line x equals a is going to be called a vertical asymptote of the graph of a function f if at least one of the following statements is true. So we can have the limit of the function as x goes to a being equal to infinity or minus infinity, or one of the one-sided limits may be equal to infinity or minus infinity. If any of those statements is true, then we are going to have a vertical asymptote. I want to point out that vertical asymptotes, they may occur when the denominator of a function is equal to 0. Like I said, vertical asymptotes, they can occur when the denominator of a fraction is equal to 0. So let's consider this example, and let's find the vertical asymptotes of this function. So factoring the denominator gives us x minus 4 times x minus 1, and it's going to be equal to 0 when x is equal to 4 or when x is equal to 1. So to find the vertical asymptotes, we have to check the limit of the function as x goes to 1 and to 4, or we can simply find the one-sided limits. Let's begin with the limit of f of x as x goes to 4 from the right. So we can also factor the numerator, and this is going to give us x plus 3 times x minus 1 over x minus 4 times x minus 1. Then as x goes to 4 from the right, the first term of the numerator is going to go to 7. The second term of the numerator is going to go to 3. And in the bottom, in the denominator, as x goes to 4, x minus 4 is going to go to 0. But because x is going to 4 from the right, when we replace numbers that are bigger than 4, this, uh, this, this expression x minus 4 is going to approach 0, but it's going to be positive. And as x goes to 4, x minus 1 is going to go to 3. So we are dividing a number that is positive in the numerator by a number that is approaching 0 but is bigger than 0. So we conclude that this limit is going to be equal to infinity. Now let's take a look at the other limit. Once again, we can factor the numerator and the denominator. But now, because we have x minus 1 in the numerator and in the denominator, they can cancel each other. And then we're going to be left with the limit as x goes to 1 of x plus 3 over x minus 4. And then simply plugging x equals 1 in the numerator gives us 4, and plugging x equals 1 in the denominator gives us minus 3. So the final answer is going to be minus 4 over 3. Well, notice that the limit of the function as x goes to 4 from the right is infinity. So x equals 4 is going to be a vertical asymptote. But the limit of the function as x goes to 1 is equal to minus 4 over 3. So the one-sided limits, they are going to be also equal to minus 4 over 3. So none of those are going to be equal to plus or minus infinity. So x equals minus 1 is not going to be a vertical asymptote. So the conclusion is that x equals 4 is a vertical asymptote, but x equals 1 is not. Let's take a look at one more example. Now we want to find the vertical asymptotes of the function f of x equals secant of x. So remember from trigonometry that by definition, secant of x is the same thing as 1 over cosine of x. So we may have vertical asymptotes when cosine of x is equal to 0. We also know from trigonometry that cosine of pi over 2 is equal to 0. So let's take a look at one of the one-sided limits of secant of x as x goes to pi over 2. Let's consider the left side limit. So as x goes to pi over 2 from the left, secant of x goes to infinity. So the conclusion is that x equals pi over 2 is a vertical asymptote, or VA for short. And then if we use a similar reasoning, the conclusion that we are going to get is that any line of the form x equals pi over 2 plus n times pi, where n is an integer, is going to be a vertical asymptote for the function f of x equals secant of x. Let's take a look at two more examples. Now we are going to consider oscillating functions. In the first one, we want to find the limit of this function, sine of pi over x, as x goes to 0 using the graph. Well, let's observe what's going on as x goes to 0. It seems like the function is oscillating between minus 1 and 1, but it's not approaching any specific number. So using the intuitive definition that I gave in the beginning of this video, the conclusion is that because it's not approaching any particular real number, the limit of this function as x goes to 0 does not exist. Now let's consider one more example where we have an oscillating function, and now we want to evaluate the limit of this function as x goes to 0 from the left. Notice that even though the function is oscillating as x goes to 0 from the left, actually the graph of the function is approaching the origin. So in this case, we say that the limit of this function is actually equal to 0 because it is approaching a particular real number, which is 0. That's all for now, but stay tuned for more fun calculus videos. See you next time.